All right, the next lecture is going to begin Unit 3. And Unit 3 is an investigation about heat and heats of a reaction, how much energy comes in or out of a reaction, and also a review on gases and gas laws. So this unit covers now two different chapters. Chapters 5, which is on thermochemistry and calorimetry, and then chapters 10, which is a review of gases, a topic and unit we did cover in honors, but that was during the COVID lockdown in the spring. So if you were someone that did not do much work with gases during that time period or any, it's going to be a brand new chapter. For those of you that did, you have the benefit of going through it, and it should simply be half of this unit should again be review. All right, calorimetry is looking at how heat flows throughout a system. So if I have a reaction that gives off heat, okay, then remember we call a reaction that gives off heat. And hopefully some of you would say exothermic. So an exothermic reaction is one where the system, which in this case the system is the chemical reaction, that it gives off or it releases energy. And where does that energy go? Well, it's got to go somewhere. So if the reaction produces heat, where does it get liberated to? And that system releases energy to something called the surroundings. So when we have an exothermic reaction, the chemical reaction releases energy, and that energy then is absorbed by the surroundings, thus making them warmer. So if you think of like having a hot hands, where for those of you that might go hunting or fishing, or you're outside, you grab a packet, you open it up, and then expose it to air, and very quickly a chemical reaction occurs in the fabric bag. Well, that heat then goes out of that chemical reaction inside of that fabric piece of material, and it warms up whatever comes in contact with it. It could be the air around it, or more importantly, it could be maybe your hand that is cold, and it helps warm up your hand, be that heat that's being liberated. So what thermochemistry is and calorimetry is the study of that heat that goes between the system and the surroundings back and forth. Okay? Once both the system and the surroundings reach the same temperature, a key word you're going to start to see is called thermal equilibrium. When a system or a group of objects reach thermal equilibrium, the temperature of both the system and the surroundings is the same, and heat stops flowing between the systems because they're equal. Okay? Now, to study heat reactions, we're going to use a piece of equipment, which you can see by that picture. This is called a calorimeter. Now, there could be some very fancy calorimeters worth many hundreds of thousands of dollars, even millions of dollars. The calorimeters that the AP goes with are called coffee cup calorimetries. And the reason why, again, is it's cheap. Even districts that are struggling financially can apply students with thermometers and also coffee cups. And coffee cups do a great job because they have such a good ability to insulate and to create what's called a closed system. A closed system is one that we assume that heat does not expel out of it. Okay, it actually stays tied to the whole thing. So when we have a chemical reaction occurring, let's say it occurs in an aqueous solution, our previous unit, the heat of that reaction can then be studied as a closed, isolated system. We don't have to worry about having heat enter it or leave it because the coffee cups create a closed system that we can investigate. So again, the system is usually the chemical reaction or the objects that come in contact with one another. The surrounding is everything else around that. And if the reaction does occur in an aqueous solution, the water is what is measured. So in a lot of these chemical reactions, if it occurs in water, if we have an aqueous reaction, we are going to measure the change in temperature of the water. The water is the surroundings. So, if the temperature of the water is going up, what does that tell me? Is heat entering the water or is heat leaving the water? And we should know that heat is being absorbed, that it's absorbing heat, and that's because the reaction is releasing energy. So if the temperature of the water in an aqueous solution goes up, that is an example of an exothermic reaction because the system is releasing energy and that energy is going into the water molecules to warm the water up. So whenever we investigate calorimetry problems, what's a key thing to understand is we typically will measure the change in temperature of the surroundings because that's much, much easier to measure. What we have to just know is that the amount of heat, if the surroundings increases 20 kilojoules or 20 joules of energy, let's say it's joules, if the surroundings gain 20 joules of energy, what does it tell me about the chemical reaction, the system? It had to lose 20 joules of energy. So the system releases 20 joules of energy that the surroundings absorb. So if the temperature of the surroundings is going up, that usually tells me that the reaction is exothermic. Exothermic energy reactions have negative values. A negative sign on an exothermic reaction indicates that it has excess energy and therefore is releasing or giving off that energy to the surroundings, which will absorb it then. So positive means absorbing, coming in. Negative means coming out. Okay? Now the equation for heat is given on your green chem helper, which is Q equals mc delta T. And on your green chem helper, off to the very far right of it, you'll notice that all of these letters are told what they are. Q again stands for heat. How much energy, that's what heat is, how much energy either is being absorbed or being released by the system or the surroundings. M is mass. Capital C is called the specific heat. And the specific heat is an intensive property of a material, which means it doesn't get affected by how much of the material you have. Specific heat tells us the amount of energy that that material must absorb for it to raise 1 gram, 1 degree Celsius, or 1 Kelvin. Now, one other thing to note, because we are going to look at changes in temperature, a 1 degree change in Celsius temperature is equal to a 1 Kelvin change in temperature. So Celsius and Kelvin, for the sake of this unit, will be the same because when we do the differences in them, they'll give us the same change in temperature values. Okay? So a 1 degree, a 25 degree Celsius change in temperature would be also a 25 Kelvin degree change in temperature. They're equal, and therefore we can use them interchangeably. So you'll notice that the units on specific heat are joules per gram Kelvin, or it could also be joules per gram degree Celsius because we're looking at changes in temperature. So the specific heat for water is 4.18 joules per gram Celsius for either one of them. What that means for water is that it takes 4.18 joules of energy to raise 1 gram of water, 1 Kelvin change in temperature, or 1 Celsius change in temperature. It takes that much energy to raise 1 gram of it, 1 degree. Okay? You'll notice that of all the specific heats given in this table, water by far has the largest. Okay? Water has a very high specific heat, even though it is a very small molecule and a very simple molecule. Does anybody know why? What causes water to require so much energy to warm it up or to cool it off? What causes that large specific heat? If anybody said IMF, you're correct. Water has a very high IMF. It contains lots of hydrogen bonding. And because it has lots of hydrogen bonding, there's a lot of strong intermolecular forces that holds the molecules together. So to cause a change in their energy or their temperature, it takes a lot of energy to do that. Metals, you'll notice, tend to have quite small specific heats, and therefore it doesn't take a lot of energy to heat them up, and it doesn't take a lot of energy also to cool them down. So metals will heat up quickly and also cool off quickly. Water will retain its energy quite well. And that's why the lakes and ponds right now in Wisconsin, it takes a lot of cold nights to drop the temperature of water that heats up throughout the summer. And it takes a lot of cold nights before eventually we'll start to see our ponds and lakes start to freeze again. a lot of energy has to be expelled from it, released from it, into the cold air to cause it to eventually to freeze. Okay? So specific heat is dependent upon the material. It's a quantity that will be given to you in any problem. You just have to know how to use the equation. So a lot of the math in this first unit, or this first, I should say, homework set is going to be a lot of just plugging into this formula. So it says how much heat is needed to warm 250 grams of water from 22 degrees Celsius to 95 degrees. Again, heat is given by the variable little q. So this is nothing more than a plug and chug problem in which we are going to plug in all the different variables. Now, what students tend not to do a very good job on this is most usually they can identify what equation to use, but what they forget to do is they should include units of measurement with their numbers. So we have 250 grams. The specific heat of water is given to us in the table, 4.18 joules per gram. Now we're in Celsius, so I'm going to use Celsius here so that it cancels, because again, it's a change in temperature. And then don't forget, to do a change in temperature, it must always be final minus initial. So 95 degrees Celsius minus 22. Now you could figure out what the Kelvin temperature for each of these is and subtract, but it's pointless to do so because a Celsius change in temperature is equivalent to a Kelvin. So now I'm just going to go ahead and punch it into my calculator, and I get a Q value of 76,285. Now, what students struggle with here is units. What units do I have left? Well, we have a gram and a gram divided by. So there's a gram on top and bottom, they cancel. And we have a change in temperature that's going to be in degrees Celsius. Again, we have top and bottom, they cancel. This is going to be given to us in J, which is joules. A capital J is an energy measurement that we use in science. Now, whenever we have a measurement in class, we should always round it to 3 sig figs, which would be to the 2. So the final answer should be 76,300 joules of energy. You'll also notice that it is positive. We get a positive value. We could have a negative value. What does a positive value in this Q mean? This means that the heat, the energy, is being absorbed. The water is absorbing. That much energy is coming into this water, 76,300 joules of energy. So this unit is very important that you have the correct sign on these measurements. Okay? Positive and negative, you might have the correct numerical value, but if it's supposed to be negative and you have positive, you're going to lose that point. All right, turn the page. So how much heat is needed to raise 50 grams of copper from 20 degrees Celsius to 30 degrees Celsius? The specific heat of copper is 0.386 joules per gram Kelvin, or joules per gram degrees Celsius, depending upon what your temperature measurement is in. Okay, so go ahead and give this problem a try. Pause my lecture for a second and see if you get the correct value. All right, you should have gotten 193 joules of energy is absorbed. And again, it's a positive value, which again means that the copper is absorbing this much energy. Negative would simply means released. Negative doesn't mean less or small. It just means is energy coming in or out. Because it's positive, this is telling me that the energy is coming into the material. Therefore, the surroundings around the material must be warmer, and therefore that energy is going into the piece of copper. All right, so what happens? Now, those are when we have just a one object system. What happens when we put multiple objects together? So here's a situation. We have a piece of aluminum that is in boiling water, and it's placed into a calorimeter that contains a different set of water that's at roughly room temperature. So if you think of that calorimeter, we have water in here, and we're going to place inside of it this very hot piece of aluminum. So we're creating a closed system here. So what do you think is going to happen with that hot piece of aluminum in that colder water? Well, what happens is that that chunk of aluminum metal will start to radiate energy from it, and that goes into the water. So the temperature of the water is going to go up, and the temperature of the aluminum is going to go down. So the water is going to gain thermal energy or heat while the aluminum loses it. But there's a very important law in thermodynamics. It's the first one. And the first law of thermodynamics is the law of conservation of energy. Just like the law of conservation of mass, the law of conservation of energy tells us that energy is not lost or gained, okay, in a closed system, but it simply changes form. Okay? So the amount of energy that the water gains plus the amount of energy that the aluminum loses, if I were to add them together, what are they going to summate to? Answer is 0. There is no change. It adds up to 0 because there is no loss or no gain of energy throughout the closed system. Okay, it just simply changes form. Energy goes from the hot object always into the cold object. And that heat flow will continue until the object reaches the same temperature. And that temperature is called thermal equilibrium. When things reach that thermal equilibrium value, energy stops transferring from one object to the next, and they stay at the same exact temperature. All right, since these are Q values, this would be mc delta T, so the mass, specific heat, times the change in temperature of the water plus the mc delta T of the aluminum will summate to 0. So whenever we have these types of problems, we have a hot object put in a cold object in a calorimeter, this is the working equation you're always going to utilize. Now it simply becomes plug and chug. All right, so we have 100 grams of water that has a specific heat on the previous page of 4.18 joules per gram Celsius. The final temperature of the water reaches 32.9 degrees Celsius minus the initial temperature of the water is 22.4 degrees Celsius. Plus, the mass of the aluminum is 75.25 grams. We don't know the specific heat of the aluminum, so that's going to be our variable that we don't know. That's what we're going to solve for. Times, again, the final temperature is 32.9, that's thermal equilibrium, minus 99.3 degrees Celsius. All right, so in the first part of the problem, 100 times 4.18 times 32.9 minus 22.4, and we get 4,389 joules. It's a positive number. Since there is a positive change in temperature, the water absorbs that much energy. Okay, all of these numbers over here are multiplied together. So 32.9 minus 99.3 gives me a negative 66.4 degree temperature change times 75.25 gives me a value of negative 4,996.6. Okay? And that would have units of grams degrees Celsius times capital C, which is my specific heat of the aluminum. So I've got roughly 4,389 minus 4,996.6 C. We now need to solve this equation for the specific heat of aluminum. To do that, we'll move one of the terms over. So I'll move this negative term over, and that's going to give me positive 4,996.6 grams per degree Celsius times the specific heat of aluminum. You could just have that be X. Solving for X, or the specific heat of aluminum, we'll divide by 4,996.6. And again, I'm using my units here. So you'll notice that when I'm done here, my units on the specific heat will have joules divided by grams degrees Celsius, which is what we typically see the units of specific heat in. Again, it can either be Celsius or Kelvin. So 4,389 divided by 4,996.6 and we get a specific heat of aluminum of 0.878. I'm going to round to 3 sig figs, so I'm going to stop at the 8 joules per gram degree Celsius. So the specific heat of aluminum is 0.878 joules per gram degree Celsius. Okay? All right, if you want to pause the lecture, now go ahead and try to do problem D, which is a similar problem, but we're solving for a different variable. Instead of the specific heat, we're going to be solving for the final temperature. So pause the lecture, which I'm going to do too, because I want to make sure to make this video not so long. And the next time you hit play, you're going to see all my work to the final answer. But pause it now and see if you can figure out the final temperature. All right, for those that could do the math now, in years past, students usually really struggled with this type of problem. The algebra skills are a little bit weak for some students that haven't done a lot of this. So when you plug it in, you have the mass. I'm going to change the color here. The mass of the iron is 5.87. Specific heat is 0.45. Final temperature minus its initial temperature, 285. We have to multiply these two together, which gives me a number of about 2.64. And I then have to distribute 2.64 times TF and 2.64 times negative 285, and we get negative 752.8. We do the same thing for the water. We multiply the mass by the specific heat, which ends up being around 230, 229.9 to be exact, and then we again distribute, and we get 230 times TF minus 3,450 roughly for the second term. Now, lastly, we need to group like terms. So the two TF terms I can keep on the left side, and I group them together and add them together, and I get about 232 times TF, final temperature. And then the other two terms which are like, I move over to the other side to make positive. Again, it's like just doing an algebraic equation, just with ugly numbers, and I get 4,201. Solving for TF, last step always in algebra is to isolate TF by dividing, and that gives me a final temperature of 18.1 degrees. So the iron will change its temperature (285). It's going to change its temperature about 267 degrees Celsius. It's going to drop almost 267 degrees Celsius. The water has literally changed its temperature by going up by about 3 degrees. Here's the misconception. Here's the conceptual question. Okay, the question will be, since the water did not change its temperature very much, okay, it must have a very low specific heat or something to that effect. Or they'll ask questions like, because water changed its temperature so little, iron, okay, has a greater change in energy than what the water does. And the answer to both those questions is the amount of energy that is changed is exactly the same. The amount of energy that goes into the water from the hot iron is the same amount of energy that the iron loses. So the amount of energy gained by the water is equal to the amount of energy that the iron loses. Why do they have such a different change in temperature then? And that's for a couple different reasons. First of all, the mass is different. We have about 10 times more mass of water. Okay? And the second thing to consider is its specific heat. It takes a lot more energy to heat up water than it does to heat up iron. So because of all those different variables, water only has a very small change in temperature of 3 degrees, while the iron changes drastically. So one key thing you have to remember is the amount of energy that changes from the hot to cold object is always the same. The reason why their change in temperatures might be different is because they usually have either different masses or different specific heats. Sometimes both, sometimes not. I've seen year in, year out questions on the national exam where they'll say equal masses of iron and water are mixed together. The iron is hotter than the water. The iron changes temperature more than the water. Okay? And then I'll ask questions about it. The reason why the iron changes more than the water is because its specific heat is smaller. So the object that has a smaller specific heat will tend to change its temperature more than the object that has a higher specific heat. But the amount of energy that changes from the hot object to the cold object is exactly the same. All right, so that is your introduction to calorimetry, where you're calculating the amount of energy in an object, positive meaning it's absorbed, negative meaning it's released, and then also some of these problems where we have a hot object placed in a cold in an isolated calorimeter and being able to calculate some variables from that. Okay, there's a worksheet in Canvas that I'd like you to do. Next week you'll have a quiz on calorimetry problems, including stuff like this. And so do the homework problems as practice before the test, which will be next week. Again, thanks for listening.